Morning. As you can see, I'm not in my usual place today. I had to fill in for somebody today, so I'm up in my office, and so we're going to record from here, I guess. So today's going to be a little more formal, so sit up a little straighter, go brush your hair. You look kind of a mess. And come back, and we'll take care of it from there. So today we're in Chapter 7, so let's talk a little bit about Chapter 7. Chemical bonding and molecular geometry. Okay, now you know how to do electron configurations. Let's start talking about shapes of molecules and bonding. All right, and so where are we going to start? Well, let's start with what we call Lewis dot structures. Okay? A Lewis dot structure, or a Lewis structure, shows the distribution of the outer, or what we call the valence electrons, in an atom, molecule, or polyatomic ion. Basically, your valence electrons, your outer electrons, it's the number of electrons in the outer S&P sublevel. That's basically what it comes down to. And don't worry, there's a really easy way to tell without writing electron configurations. Unshared electrons are shown as dots. Bonds are shown as straight lines. How does all this work? Well, let's say I've got a hydrogen atom here, and I want to draw the Lewis symbol for hydrogen. Well, what I do is I look in the periodic table, and I simply look for the element in the periodic table, and all I do is I really just look at the group number. So for hydrogen, for example, I would look and see where hydrogen is. Here it is in group 1. So basically I just do hydrogen and draw one dot. That's it. It's that simple. Okay, where's fluorine? Well, fluorine is over here in group 17. So remember, for your outer electrons, well, you don't remember, for your outer electrons, if it's group 1, 2, something like that, it's just the group number. If it's a team, cover up the 1. Okay, if you have a periodic table that goes 1A, 2A, 3A, 4A, 5A, whatever, it's just the number. But chlorine or fluorine here is in group 17, so we cover up the 1, and so it has 7 valence electrons. Right? That's all you got to do. Now, technically, it's this 2s2, 2p5 is what it is. But see, you don't even have to know that. All you have to do is just look at the group number it's in. And so all these elements here would have 7 valence electrons or 7 outer electrons. Does that make sense? So I'm going to write the symbol for fluorine. I'm going to put 1, 2, 3, 4, 5, 6, 7 dots. That's it. It's got to be able to count. Okay? Now, generally speaking, what you'll find is most atoms and molecules prefer to have 8 valence electrons. Why 8? What's so special about 8? Well, because look at your noble gases over here. Your noble gases all are in group 18, so they all have 8 valence electrons, except for helium, of course. You've got 1s2. That fills up the first energy level, so 2 electrons there for the helium. But remember, we said that if your outer S and P's are full, then that makes an atom really stable, and that's why your noble gases are so stable. They don't react with anything. Well, how many electrons can I fit in an S sublevel? 2. How many electrons can I fit in a P sublevel? Well, 6. What's 2 plus 6? There you go. There's your 8. Okay? And that's called the octet rule. Okay? And the octet rule states that, generally speaking, an atom is stable when it has 8 valence electrons around it. Exception to the rule, hydrogen, which is happy with only 2, because, see, that gives it a nice stable configuration just like helium. Okay? So let's go back and see what we've got, our little situation here. So here's a hydrogen with 1 valence electron. Is it happy? Well, no, it'd rather have 2. Here's a fluorine with 7. Is that 8? No. Is it close to 8? It's close to 8. Does close count here? No. Close doesn't count here. So this fluorine needs another electron. This hydrogen needs another electron. So the hydrogen says, tell you what, I will share my electron with you if you'll share an electron with me. And so that's exactly what they do. They share this pair of electrons. Now notice that the number of electrons here, I've got how many electrons? I got a total of 8. Count how many I have here. Make sure I'm not trying to pull some sort of magic trick on you or anything like that. How many valence electrons do I have here? 1, 2, 3, 4, 5, 6, 7, 8. Okay? How many electrons do I have around this hydrogen right here? Well, I have 2. Stable? electron configuration as helium, right? How many electrons do I have around this fluorine? 2, 4, 6, 8. Stable? Yes, because it's got 8, just like a noble gas. So, things don't happen in chemistry just for no reason. They don't just randomly happen. If they did, then there'd be no predicting things, and I'd be out of a job because, your guess would be as good as mine, right? So, what is the driving force? There's got to be some reason why that hydrogen and that fluorine decide to share those electrons. There's got to be something to be gained. What's to be gained? Well, each atom has a nice noble gas structure, and so each atom is happy. If each atom is happy, is the molecule happy? Yes, the molecule is happy. What charge do I have here? I have no charge. So see, I'm not violating the principle of neutrality. So this is called covalent bonding. We talked about ionic bonding, why some things will give up electrons and take electrons to have that nice noble gas structure. The downside was they had a charge. All right? And so what would happen is these charged ions would come together and form ionic compounds, which were electrically neutral. And that's ionic bonding. In covalent bonding, you're accomplishing the same thing, you're just accomplishing it in a different way. In covalent bonding, you're sharing electrons. But really, the driving force behind ionic bonding and covalent bonding is really the exact same thing. You're trying to get a nice noble gas structure around all the atoms. What Lewis said, he said, well, I've got atoms with 47 electrons. Do I have to really look at all 47 electrons? No, what I can do is I can simplify. Instead of looking at the inner ones, which is nice to know how those are put together, where the bonding is going to occur is out here at these outer electrons, where those electrons touch. So if I can just look at the outer electrons, then I can get some sort of a sense of how things bond. And that simplifies things. And that's the whole driving force behind Lewis dot structures. Make sense? Now, when we have a shared pair of electrons like this, sometimes what we do is we represent that with a straight line. Okay, and this is what we call a single bond. And a single bond is a shared pair of electrons. So whenever you see a line in a drawing of a molecule, that's 2 electrons that are being shared. And we call that a single bond. Make sense? Okay. Well, here's a hydrogen atom. How many valence electrons? Well, group 1, 1. Here's another hydrogen atom with 1 valence electron. Okay. Here's an oxygen atom. How many valence electrons would an oxygen atom have? Well, let's look at the periodic table. Looks like it's in group 16. So cover up the 1. How many valence electrons? 6. Now it has 8 electrons. But are we putting all the electrons in? No, you're just putting in the valence electrons, which essentially is your outer S&P. So basically for oxygen, it's 1s2, 2s2, 2p4. So it's basically that 2s2, 2p4. Those are your 6 electrons that are going to be shared. But again, you don't even have to be able to write electron configurations, which you should be able to by now. But you don't even have to do that. All you have to do is look at a periodic table and see what group it's in. And you'll always have a periodic table on the test. So not the total number of electrons, look at the group number. You're just looking at the valence electrons. All right? And so that's why we've got an oxygen here drawn with 6 dots. 1, 2, 3, 4, 5, 6. Do they have to be around the oxygen a certain way? Nope, don't really care. Okay? I drew it that way for a specific reason, but I'm looking for 6 dots. If I see an O and I see 6 dots, I'm happy. That's what I need to see. Okay? All right. How many total electrons do I have over here? Well, I've got 1 here and 1 here and 6 here, so I've got a total of 8, right? Okay? So this hydrogen here shares an electron with this oxygen. This hydrogen shares an electron with this oxygen too, and they share those pairs. So how many electrons do I have in this little structure? 2, 4, 6, 8. So you start with 8, end up with 8. Conservation of matter. Okay? How many electrons do I have around this hydrogen? Well, I have 2. Stable? Yeah. It's like helium. How many do I have around this hydrogen? 2. Stable? Yes. How many do I have around this oxygen now? Well, I have 8. 2, 4, 6, 8. Is that oxygen atom stable? If every atom in the molecule has a noble gas structure, would you expect that molecule to be stable? Would you expect a compound to exist with 2 hydrogens and 1 oxygen together? Yes, you would. Does it exist? Yes, it does. What do we call it? Well, that would be water, H2O. And that's why the formula for water is H2O and not H3O, or H2O3, or HO4, or H6O2. That's why it's H2O. Because by putting together 2 hydrogens and 1 oxygen, you get something where every atom has a nice noble gas structure, so therefore the molecule is stable. Okay? Each one of these pairs of electrons here and here being shared, so what we can do is we can represent that with a line, like this. So every time you see a line, think 2 electrons. So 2, 4, 6, 8. Make sense? Now notice what you've just done. You've just predicted that a compound ought to exist between hydrogen and oxygen that contains 2 hydrogens and 1 oxygen. And you just predicted that that ought to be a stable compound. When you go into the laboratory, is that what you see? That is what you see. And see, that's what theories do. Theories are tools. They are tools to predict and explain the world around you. Theories, number one, have to make predictions. If you have a theory that doesn't make any predictions, it's like a tool it's like a socket wrench that doesn't fit anything. You might as well just throw it away. But those predictions also have to come true. So here is a theory. You've just predicted a compound ought to exist between 2 hydrogens and oxygens. When you go out into the real world and you look around, what do you see? You see H2O everywhere. So yes, it is stable. And the theory explains why it's stable, why you see what you see. All right? Now, how much math did you have to do this? Did you have to do any calculus here? Did you have to do any matrices, find determinants? Did you have to find like any gradients or curls or differential equations or integrate by parts? What did you have to do? Did you have to use expensive equipment? Did you have to buy yourself a $130,000 NMR? Did you have to use the hours? Did you have to train and learn how to run an atomic absorption spectrometer or an ICP? Did you have to do any of that? What did you do? Well, you had to be able to count to 8, and you had to be able to draw dots on a piece of paper with a pencil. 5-cent piece of paper, 25-cent pencil. And you did it in about 15 seconds. See, if you can come up with theories that are, number one, simple to understand, easy to work with, and number two, cheap, which is nice. You don't have to spend a lot of money in education to try to understand it, and you can do them very quickly, those are good tools to have around. Those are handy things. That's that little adjustable wrench that you use all the time. See? And that's what Lewis dot structures do. It's a very simple tool. Is it too simple? Well, we'll talk about it. But it tells us a lot of things. It's a very useful theory to help us understand how covalent bonding works. And that's that's what covalent bonding is. It's the same driving force as ionic bonding. Put those ions together, get something that's neutral, doesn't violate the principle of neutrality. Share electrons, put something together that's neutral, doesn't violate the principle of neutrality. So it's another way that atoms can come together, get the nice noble gas structure, and have that principle of neutrality satisfied at the same time. All right? Okay, well, in H2O and HF, as in most molecules and polyatomic ions, non-metal atoms, except hydrogen, there's always an exception to the rule, isn't there, are surrounded by 8 electrons, or what we call an octet. Okay, that's called the octet rule. In this sense, each atom has a noble gas structure. Okay, when people try to draw Lewis dot structures, what they will attempt to do generally is they will attempt to do what I call the jigsaw puzzle method. You pour out all those pieces of that jigsaw puzzle on the table, and you just start trying to fit together pieces kind of at random and kind of hope they fit. How long does it take you to put together a jigsaw puzzle? Well, it takes forever because you get all these pieces, and You know, they all look the same. You know, I've seen jigsaw puzzles where like every single piece is red. You know, and I've seen jigsaw puzzles where every single piece is exactly the same. They all fit together, but you got a picture on one side, and then the picture on the back is the same picture rotated like 90 degrees. Yeah, I'm not doing that. But yeah, I mean, they can get kind of tough there, right? Well, for very small molecules, the jigsaw puzzle method kind of works. You can get away with it. It's like, you know, that jigsaw puzzle with the states of the United States that you had when you were a kid. You can kind of put them together and somehow get it. But, you know, a 2,000-piece jigsaw puzzle, that's probably not a good strategy. You need to have a strategy. Well, that's kind of the same way it is with drawing Lewis dot structures. For small molecules, you can get away with the jigsaw puzzle method, but when the molecules get larger, it doesn't work very well at all. So what I'm going to do is I'm going to give you a stepwise procedure to draw Lewis dot structures, which should help you on your lab that you're doing. And, you know, what could possibly go wrong? Well, there's really only two things that could go wrong when you do this. I'm going to show you what to do if the first thing goes wrong. I'm going to show you what to do if the second thing goes wrong. And so you're covered, because those are the only three things that can happen. It can work. One thing could go wrong or the other thing go wrong. If I show you how to fix those, there's nothing I can throw at you on the test that you can't do, is there? All right? This is kind of important because everything else in the chapter and also the next chapter keys on you being able to draw Lewis dot structures and draw them correctly. If you cannot draw Lewis dot structures, you are dead in the water. You've got to get this down and be able to do it with some regularity. Okay? Fortunately, it's not that bad. Again, no calculus involved here. You just got to be able to add and count to 8. Can you add and can you count to 8? Of course you can. You can do this. All right? Okay, well, let's go over the rules first. And of course, it will make a lot more sense when we do one, but let's just go over the rules just to have it all in one spot, right? In our notes. So, rules for writing Lewis dot structures. And this is the single bond case. We'll talk about the exception there in a minute. First thing you're going to do is you're going to count the number of valence electrons available. Okay? Instead of doing the jigsaw puzzle method, what you're going to do here is you're going to use a different strategy. It's kind of like building a building. You know, this building they put up 10 or 15 years ago, I guess. Seems like the years just keep going by. About $8 million. How much this one costs? This side actually cost $8 million. You can't throw up anything for less than $8 million these days. And if you were here 8 or 10 years ago, what you would have seen is a bunch of girders going up. You know, when you build a building, you put the carpet down and put the furniture in first, and you build the building around it. Well, no, that's not the way you build a building. You know, the first thing you do is you pour the foundation, right? Got to have a foundation to have the building. So, you know, $8 million is a lot of money, and I don't happen to have that lying around, but fortunately there are people in town that actually do. And so what you do is you go to maybe one of your donors or benefactors and you say, you know, we're building a new science building over at Midland College, and, you know, if you could, you know, see fit to donate a certain amount of money, you know, maybe we name it after you, maybe we name a hall, or we put your name on a plaque or something like that. You know, there's people that, you know, just have that kind of money. They'll just write out a check, say, here you go, you know, go build your building, okay, which is kind of nice. So, let's say you're building a building, and you're pouring concrete for the foundation. So, you're in your pickup truck, you're going to Home Depot, you get yourself a load of concrete, you know, about $500. So, you go to your donor and say, hey, going to Home Depot, need some concrete. Can you write me a check for $500? And so they write you a check. You go to your concrete, you pour that. Well, you know, a lot more concrete's needed than that, so I guess you got to go back to Home Depot. So, you go back to the guy and you say, hey, I need another $500 check. You know, we're going back to Home Depot, and maybe he writes you another $500 check. Well, you dump all that out. Now you got to go back to Home Depot for more concrete. So you go back to the guys, ask him, hey, I need another $500. Do you think that's the most efficient way to do things? How many times do you think you'll show up on his porch before he stops answering the door? Maybe 2. maybe 3 if you're lucky. All right. Probably not the most efficient way to do it. The most efficient way is to say, hey, we're building a building. If you could see fit to donate $100,000 or so, there's people in this town with that much pocket change, sitting on their outside table. Maybe we name a hall after you, or an instrument, or put a plaque up, or something like that. And so you get that $100,000 check, you put it in the bank account, and then when you need to go to Home Depot, you start writing checks on that account. Don't you think that would be a more efficient way to build a building? Well, that's the exact strategy we're going to use when it comes to building a molecule. Okay? Instead of saying this atom has this many valence electrons and that atom has this many valence electrons, and we're going to keep them apart there, what we're going to do is we're going to take all the valence electrons available and we're going to put them in one big giant pile. All right? And then what we're going to do is we're going to start doling them out from the pile. And that's a much more efficient way to build a molecule, just like it's a more efficient way to build a building. So the first thing you're going to do is you're going to count the number of valence electrons available. Okay? The number of valence electrons contributed by a nonmetal atom is equal to the last digit of its group number in the periodic table, as we talked about over here. If it's a team, over here it's just 1 and 2. By the way, these elements here in the middle, the last electrons in these elements, this is what's called the what block? The D block. This is the F block. If the valence electrons are the last outer S's and P's, do you think this works really, really well for elements in here? Horrible. Okay? So we are probably going to combine ourselves to maybe over here, but actually mostly over here, nonmetal atoms, because those are your covalent compounds, your 2 nonmetal atoms reacting. So most of our Lewis dot structure stuff is going to be confined over here. We're going to spend a lot of time over here. Over here, since you've got d orbitals, you need another theory which is more sophisticated that you really don't want to see right now. All right, so we won't worry about transition metal chemistry at this point. All right, so count the number of valence electrons available. The number of valence electrons contributed to a nonmetal atom is equal to the last digit of the group number in the periodic table. If you have a negative charge, because this works for ions as well as molecules, you're going to add electrons. If you have a positive charge, you're going to subtract electrons. All right? So if you have something with a -3 charge, you're going to add 3 electrons. And the reason why is because that -3 charge says, hey, there's 3 more electrons in this structure than there ought to be. And that's why it's got a -3 charge. If I had something with a +2 charge, then I'm going to subtract 2 electrons. Because that says, hey, there's 2 less electrons in this structure than there ought to be. Electrons have a negative charge. That's why we're adding if the charge is negative and we're subtracting if the charge is positive. Okay? It's neutral. We just count them up and we don't worry about it. Okay? All right, so you're ready to build your building. So you got the foundation down. Does the carpet go on next? Well, no. If you were here 10 years ago, what you would see is you would see girders going up. You see people welding and all sorts of stuff. You build the kind of the skeleton, the outside, the rafters and things like that first. That's what goes up. Well, that's exactly what you're going to do with your molecule. You're going to draw a skeleton structure using single bonds. Okay? If you have a skeleton crew working down at the factory, that's the bare minimum number of people you can have to keep the thing running. Well, a skeleton structure is basically the bare number of electrons you can have to build a molecule. It's the skeleton of the molecule. So how do I do that? Well, generally speaking, for what we call one-center molecules, which is all I will probably throw at you on a test, is you're going to put one atom in the middle, and the rest of the atoms are going to go around the outside, kind of like spokes around the wheel. So the question would be, what goes in the middle and what goes on the outside? Well, the central atom is usually written first in the formula. Is it always? No, but generally speaking, that's the way it works. It's the one that's the least electronegative. Yeah, we'll talk about it later. But usually it's the first atom in the formula. All right. Your terminal atoms, terminal means outside. I don't know why I didn't just put outside, but I did. I keep having to explain what terminal means. I don't know why I did that. Terminal atoms are most often hydrogen. It's got to be a hydrogen. Hydrogen has to be on the outside because I can fit how many electrons around a hydrogen? Well, 2. See, and so I can't put things around a hydrogen. So we know hydrogen has to be on the outside. Oxygens are generally on the outside, Halogens are generally on the outside. What are your halogens? Well, that's group 17. That's your fluorine, chlorine, bromine, iodine, so on and so forth. Okay? When it's all said and done, carbon almost always forms 4 bonds. You know, I can only think of one molecule where carbon doesn't form 4 bonds, and I teach organic chemistry. That molecule happens to be carbon monoxide. It's a carbon with a triple bond to an oxygen, and so you actually only have 3 bonds around the carbon there. But honestly, I can't think of another carbon-containing molecule that doesn't have 4 bonds. It just always has 4 bonds. All right? So if you draw your structure and you get to the very end and it doesn't have 4 bonds and it's not carbon monoxide, you might want to take a look at it again. Okay? All right. So you've built the structure. You've built the skeleton structure. You got to pay for it now. So you're going to write a check. All right? You're going to deduct 2 electrons for each bond in the skeleton structure, because each of those bonds, remember, is a shared pair of electrons. All right. Then you may or may not have some electrons left over. If you don't, and you've got 8 electrons around everything, I guess you're done. But if you have electrons left over, what you're going to do is you're going to distribute the remaining electrons to the outside atoms first, giving each atom a noble gas structure. Whatever is left over, put it on the central atom. Now, why in the world would I do something like that? Well, because what you're going to do is you're going to run into some exceptions to the rule. But when you run into exceptions to the rule, the exceptions are always in the middle, not around the outside. Generally speaking, the ones out on the outside always kind of follow the octet rule. There are exceptions to the rule, but it's going to be that central atom. So fix the outside ones first. Whatever's left over, just pile in the middle, and there you go. It's like once I've got my building built and I've got the framework, well, now I can get the bricklayers and, you know, put in the walls, and I can start putting carpet and furniture in. That's kind of how you do it. So, yeah, building molecules kind of like building. Right. This makes a lot more sense when we do it. So, tell you what, let me give you a couple of examples here. So, let's start out here. This is CHCl3, that's trichloromethane, systematically. This is also known as chloroform. This is chloroform. What do we use chloroform for? Knocking people out, right? Well, that's it. That's the stuff. CHCl3. Right. Can you draw me the structure for CHCl3? All right. Well, let's see. I've got a carbon atom. What group is that in the periodic table? Well, that's in group 14. So how many valence electrons? 4. Now, it's got 6 electrons, but again, we don't care about all the electrons. We just care about the outer S and P. So it's just those 4 that are participate in bonding. The 1s2 inside not gonna participate in bonding. Okay? So there's 4. Okay, I've got a hydrogen, 1 hydrogen here, and 1 electron. So that's 1 electron there. And I got 3 chlorines. How many valence electrons does chlorine have? I've got 7 because it's in group 17. And I've got 3 of them. Do I have a charge? No charge. Okay. So 4 plus 1 is 5. 3 times 7 is 21. What's 21 and 5? 26 electrons total. So I have 26 electrons total to work with here. Okay, so how am I going to use them? Well, step 2, we're going to draw a skeleton structure. So first atom in the formula, usually the central atom. The rest of them go around the outside. So we're going to put our carbon here in the middle. And we're going to, hydrogens and halogens generally are outside atoms, so we're going to put these around the outside. Does this seem like a reasonable skeleton structure? Reasonable. Okay? Step 3, deduct 2 electrons for each bond in the skeleton structure. So how many electrons did I use to build this thing? Well, each of these lines represents what? 2 electrons. It's a shared pair of electrons. So I used up how many? 2, 4, 6, 8. So I had 26. I used up 8. How many do I have left over? I have 18. Okay, what am I going to do with those 18 electrons? Well, they're going to distribute around the outside atoms first, and whatever's left over, put on the inside. Do I need to put any around the hydrogen? No, because see, I've already got 2 electrons around the hydrogen. It's already happy. So 1, 2, 3, 4, 5, 6. many electrons around this chlorine? 2, 4, 6, 8. Stable? Yes. How about this chlorine? 2, 4, 6, 8. How about this chlorine? 2, 4, 6, 8. How about this carbon in the middle? 2, 4, 6, 8. Every atom in the molecule has a nice noble gas structure, and so every atom is nice and stable. There you go. You just draw the dot structure. Try another one. Okay. Here's an SO3 2 minus. Okay. What's an SO3 2 minus? It's a polyatomic ion you're supposed to know. This is a sulfite. Not sulfate, it's an SO4. Sulfite polyatomic ion. It's got a -2 charge. You ever wonder why your polyatomic ions have the charges they have? You know, why does a sulfite have a -2? Why isn't it -3 or +1 or -6? Is there a way you could predict that? Actually, there is. Let's draw the dot structure. So I've got sulfur. What group is that in the periodic table? That's in group 16, which is periodic table. So it's got 6 valence electrons. I've got oxygen, which has how many valence electrons? Well, it's got 6. How many oxygens do I have? Well, I have 3 of them. All right, so 3 times 6 is 18. 18 and 6, 24. What do I do about this -2 charge? Well, this -2 charge says there's 2 extra electrons somewhere in that structure. Okay, do you have to know where they are? No. Are there places where they're more likely to be than others? Actually, there are. That's a concept called formal charge, and we'll talk about it later. But all you've got to know is there's 2 extra electrons in there. And so that's why we added 2 here. See, this is neutral, so I didn't add anything. Okay? So this is 24. 24 and 2 is what? 26? There you go, 26 electrons. By the way, it doesn't always add up to 26. It just did for these 2 examples. All right, so what do we do second? Well, we're going to draw a skeleton structure. First atom is generally the central atom. Oxygens are generally outside atoms, so maybe the sulfur in the middle with the 3 oxygen atoms here. Make sense? Okay. How many electrons did I use up when I drew this? Well, I used up 2, 4, 6. So I had 26. I used up 6. How many do I have left? I have 20 electrons left. What am I going to do with those 20 electrons? Put them around the outside atoms first, get a noble gas structure, whatever's left over, stick it on the center atom. So 20, watch me count here, make sure I'm not trying to trick you. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Got 2 left, where'd they go? 19, 20, put them on the central atom. Okay? How many valence electrons around this oxygen? 2, 4, 6, 8. How about this oxygen? 2, 1's 2, remember, 4, 6, 8. How about this oxygen? 2, 4, 6, 8. Is each oxygen happy? Yep, 8 valence electrons. How many do I have around this sulfur? 2, 4, 6, 7, 8. Is the sulfur, does it have a noble gas structure? Yes, it does. Would you expect this polyatomic ion to be reasonably stable? Yes, because every atom in the polyatomic ion has a nice noble gas structure. Why does a sulfite have a -2 charge and not a -1 charge or a +2 charge? Because to get the noble gas structure, you've got to somehow add 2 extra electrons. And that's the reason. So see, the driving force behind many, not all, but many of your polyatomic ions is the same as the driving force behind your monatomic ions. The reason a chlorine forms a chloride is because by picking up an extra electron, it's got a nice noble gas structure. The reason a sulfite polyatomic ion forms a -2 charge is because by adding 2 electrons somewhere within that structure, every atom in the polyatomic ion can have a noble gas structure. So see, very similar driving force behind your polyatomic ions and monatomic ions. Could you sit there and derive the fact that a sulfate has a -2 charge, and a phosphate has a -3? Technically, you could. Would it take you a while? Yes, it would take you a long time. And sometimes in life, it's just easier just to know. times 2 is 4. 6 times 3 is 18. Could you sit there and tell me why 6 times 3 is 18? You probably could. But do you really need to? Or do you just need to know 6 times 3 is 18? I mean, sometimes in life there are things you just got to know. It saves you a lot of time in going back and deriving everything. And this is why I made you memorize the polyatomic ions. It's just easier to know that a sulfite's an SO3 with a -2 charge than go through drawing the dot structure, for everything. Yes, there is a reason why it's -2. It's not just randomly we didn't pull that up in there. See, I explain a lot of things. It just takes me a while to do it. Just have to keep going through the chapters. Make sense? Can you do this? Okay. Well, that's probably a pretty good place to stop, I think. So notice how everything worked out just right. We had just enough electrons to go around. Wow, that was neat, wasn't it? When you get to choose the examples, things usually work out really easy. When you don't get to choose the examples, sometimes it's a little bit harder, right? When you're having to do all that homework. What could go wrong here? Because there's probably something that could. Well, there's really only two things that could go wrong here. Okay, one thing that could happen is I don't have enough electrons to go around. Okay, can't get 8 around everything. The other thing that could go wrong is I have too many electrons to go around. And I mean, really, if you think about it, there's only 3 things that can happen. Either I have too few electrons to go around, I have just enough electrons to go around, or I have too many electrons to go around. There is no other possibility. I've just shown you what to do if you have just enough electrons to go around. So maybe in the next video what I do is I show you what to do if you have too few, and I show you what to do if you have too many. And if I show you those 2 things, there is nothing I can throw on a test that you can't do. There really is no other way I could trick you, is there? I don't try to trick you. Well, sometimes I do. Don't get paranoid. But that's it. Alright? So I guess that's where we pick up next time. I'll show you what to do when things don't work out the way they're supposed to. In the meantime, practice, draw some little dot structures. But if you follow that little stepwise procedure, I find it's a lot easier than trying to piece things together. Because, yeah, it doesn't work for larger molecules. So we'll stop there because we're running out of time. We'll continue on from there, and then we'll start talking about shapes of molecules. What is if you could hold a molecule in your hand, what would it actually look like? Is there a way that you can predict that? Actually, there is. And that's what we'll talk about later on in the chapter as well. So I guess we'll see you next time. Bye for now.